In this video, we're going to do a quick recap of linear finite element method. We start with the basic idea of FEM. Let's say we have a general continuum. It could be of arbitrary shape, it's constrained somewhere, and then it's loaded on this surface. This body, since it's continuum, has an infinite number of material points. So if we want to solve this problem, whatever solution we have, be it displacement or stress or strain, it needs to be defined on all these material points, which means that we have a problem with infinite number of degree of freedoms. Now, once the geometry of this body becomes irregular, we no longer have a nice analytical solution. With the finite element method, we replace this original problem with the approximate one on a mesh. So this mesh, we have subdivided the original arbitrary geometry into a collection of elements. So for this problem, now we have a finite number of elements, and each element has a finite number of nodes. We basically now are solving a problem with a finite number of degree freedoms. So we shifted our focus from arbitrary continuum to a regular geometry, such as an element. This here is a tetrahedron. We study how this element behaves in terms of nodal forces and stiffness of this element in terms of stiffness matrix, and then we assemble them together into the original mesh, and we reconstruct the solution over this approximated continuum. So this is a basic idea of FEM on a very fundamental level. There are some important assumptions in the linear version of FEM, and the very first one is that the displacement are infinitesimal compared to the dimension of continuum, and this means that the strains are very small, the rotations are also very small at each material point, and then the deformed domain can be approximated as the same as the initial domain. So this is why when we perform all the integration for the internal and external force vectors in the linear finite element method, we never need to worry about the integration domain. We simply integrate on the original domain of the element. With this assumption, we can use the linear strain tensor, which means that now the strain is a linear function of the displacement vector u. And in this notation, this can be written in such a form. And the second assumption is that the material behavior is linear elastic, which means that the Cauchy stress, here represented by tau, can be written as a linear function of the strain, linear strain tensor. And C is a constitutive tensor. In the finite element implementation, tau and epsilon are represented as vectors, and C is a matrix. The third assumption is that the boundary conditions remain unchanged throughout the analysis, which means that the constraints between the nodes, they remain unchanged throughout the analysis. Whenever we have contact, then this condition would be violated, because contact creates new constraints between a pair of surfaces, and this condition would not be valid anymore. And with these conditions, we could integrate our element level equation, where we would obtain Ki as the element stiffness matrix and Ai as the element nodal degree of freedom vector. The product of the two equals to Fi external, which is the external force applied on the nodes of this element. By the assembly process, we arrive at the system equation, which describes the behavior of the entire mesh. So it is also a linear function, where we have the global stiffness matrix K times the global degree of freedom vector A equals the global external force vector Fxt. By linearity, I mean that if we were to scale the external force vector by lambda, we expect to receive the same scaling in the solution, which is A.